Good evening mga Bisaya. So in this video we will be discussing about steel framing. So we will use the same building and then we will try to do a steel framing. So most of the time, like if it's like a warehouse or a shop, it will be a pre-engineered. It will be a pre-engineered building, pre-engineered metal building, and then if it's like a commercial building, it will be used or conventional conventional framing will be used. So, um, so for example, if this is a commercial building and we will use a conventional framing, we will be doing a so we can do the same layout as the wood framing like wood trusses. We will have it's already like in this particular architectural drawing, the columns are already laid out. So all you have to do is basically, as the structural engineer, is size these columns based on this layout. So the columns are here, right? Now, if this is a conventional framing, then you will have intermediate columns here, and then this one here, there's a window. Then all you can do is you will have two columns on each side of the window, and then run a granite beam here. Now, for like I said, for conventional framing, you will have interior beams along this line, and then you have perimeter beams right here. You will have perimeter beams, and then you will run the. It's usually for something like this one. It's typically a open web steel joist. So I will show you later a sample of a commercial building with frame with open web steel joist on a steel beams and columns. And then in this particular project, what I did is I combined an HSS column, like rectangular or square HSS, and a wide flange. I use wide flange for locations where the columns are like where the beam or the bending on the columns and beams is really high. And then I will show you later. So this is so in the last video we also discussed about aspect ratio, right? Aspect ratio of your roof diaphragm or floor diaphragm. So all you have to do is determine the dimension, the requirements. If you can design this as a single diaphragm, or if you have to divide. Now, if you notice, this is almost equal or the same dimensions, like length and width of the building. And if you look at the diaphragm ratio for metal deck, because this is a steel building, and if we are using a steel joist, it will be a metal deck. So for metal deck, like no, like just metal deck, 2:1 is the ratio, and then if it's a composite metal deck with concrete field, then that is 3:1. Now for roof, it's typically just metal deck and then insulation on top, and then whatever is the type of like usually torsion roof is BS membrane. So um, so you have to check the aspect ratio, and then based on this dimension, you can by looking at dimension alone, it's almost the same, like in this direction or in this dimension in this way. So you can use the entire No, you don't have to provide any intermediate lateral force resisting system because you have a diaphragm boundary. But in the, like for example, for the sake of discussion, if this is like a really long building, then you have to divide, you know, you have to provide intermediate, um, or you have to divide the diaphragm into like to meet the aspect ratio, and then you have to provide a lateral force resisting in this say for example in the, or in this line here intermediate. Then you have to, it's either design this one as a moment connections like this interior. I mean, it could be just two span or three span or just single span. Design it as a moment frame so that it can resist because here, I mean, unless you are allowed to have a, you have a cross bracing there. Now, the lateral force resisting system, we will discuss that in a separate video. Like we will discuss from wood shear wall, like tension rod, portal frame. We will discuss that separately, but this is just more of like an overview. So it's either portal frame or cross bracing, or if you have this one here, um, you can use this one as a shear wall if you have to. But considering it's a metal frame, steel building, then I think your option is either cross bracing or portal frame. So if this is now one single um, one single diaphragm, then you have to design the boundary attachment here. I already discussed a like on a separate video. It was a reaction video regarding metal deck, but in this particular series, we will also discuss like you know how like how to analyze metal deck, how to size metal decking, and how to size open rib steel joist. So we will discuss that in once we touch the this topic here. Um, loading calculations. This one. So once we touch with this topic here, because we will be discussing also load calculations and applications, like how the loads are applied into the structure itself. We will do a video on that one as well. So so now you already have a like intermediate or intermediate columns here laid out by the say by the architect. So all you have to do is run a beam in this direction, run a beam, and then size a beam. Now for the typical construction here so far for conventional framing is they will use a Gerber system. Now at first, like before, oh no, we already have Gerber system before, and I was still working at the outsourcing company in that outsourcing company. So what it means like Gerber system, if you remember at school, you will be given like a beam here, and then you will have two supports. This even came out in the board, usually in the board exam, and then the question would be what would be the maximum distance x so that the negative bending, no, the negative bending here is equal to the positive bending. Because in this framing system, it would be very economical if we do it this way, like Gerber system, like design this one so that the bending, the support is equal to the, or it may not be equal, but at least really close to the bending at midspan, so that the section will be economical. Now, how does this apply in the actual framing? Like, for example, you have here. Now, usually, what they will do is they will have this frame here, this beam. Oh, so they will I haven't done any project like this way because um most of the steel building that I used are commercial for commercial application, like commercial retail unit, and they don't want any cross bracing. All connections will be, or not all, but like I would say 95% of the connections are moment connected. So you cannot do a Gerber system if you are using a, I mean, technically you can, but I think it would be because if your frame is used to transfer lateral loads, like a strut, then your connection at the joint might be um, y- you might encounter an issue. Basically, this is what I mean. So a Gerber system, usually what they will do, I mean, this is what I've seen so far in all commercial building here. So they will extend the beam this much, and then this one, they will frame this as well as one, then extend it, and then this one also, they will extend that one. And then they will add another section here, which is really small section. It is smaller because it will be short span. Now, if you look at the elevation, what it looks like is this is your this is your beam, right? This is your column, then this is your column here, and then another beam here, another beam. And then what they will do is they will design like a smaller beam here because it is now short span. And it will be easier for erection also because they will erect this part first, then they will erect this next, and then the third is here, and then another. And the next one, it will be smaller beam also because the load on this one, this is really usually like half of the entire. If this is if this is L over or this is L, then this is usually L over two most of the time. I mean, it's not exactly L over two, but close to that. And then this will be really small, and then they will just do like a shared connection here. This is shared connected, and then the reaction from here will create a bending here, and it will be countered by the positive bending. And just, I mean, if possible, the bending here would be equal to the bending at the support so that it would be economical. So this is how usually they frame. Now, um, I don't have. Let me see if I have a picture. I don't think I took a picture. Like most warehouse here, like Canadian Tire, Walmart, Costco, they are framed this way. Maybe next time I will take a picture if nobody sees me, and then I will post it in my page. But yeah, this is how it's framed. And then the other way is if it's a moment connection, of course, you have no other option, but you have to have a column here, and then your beam. It will be moment connection. You have your um like moment plate at the top and at the bottom, and then the same here, and then you have your share connector here, share plate. So I will show you a picture um with a like steel frame. This is a commercial building. Um, so this one. So if you noticed, this one is, oh, that's shear connection. This one is shear connection. Yeah, those are shear connections, I think. Oh no, moment connection. This is not. I think this is because this project some plates were not see you see the like holes, but the moment plates were not installed. I don't know for some reason. They are field welding done. They were field welding done in this particular project. So if you notice, this is an open web steel joist, and then if yeah, so you don't see any cross bracing here because this will be, I mean, not all, but I would say 90% will be curtain wall, like storefront, like window, glass window. And then the only solid part here or solid wall is, I think, some what do you call this one, like mechanical room. And then the problem with this is in between columns there is always a window, like full height window. So there's no way. I mean, you can um put a course bracing, but the client doesn't like any bracing at all. So everything are moment connection. So that's why if you notice this one, this is it is so it looks small, but it's actually a 10 by 10 by 5/8 thick, 5/8 inch thick. So what's that in millimeter? So that's 16 mm diameter, 16 mm thick wall thickness for the this is 250 by 250 millimeter, and then this is I think W16 W21. But remember, so yeah, this is a what we call this one. This is a commercial retail unit. I think six base or one, two, three, four, five, six, seven. I think there are eight. I think eight or nine. So yeah, so this is one way of framing a like still building. Um, if there are times that instead of using steel joist, we use steel beams like wide flange. Uh, so this one here. So in this particular project, we used um, wide flange. So what we did is this is a pre-ins building, and then we sized the floor framing because this is another. This is because this project is so big. It's a like an arena, and it was because of budget constraint. It was divided into three phases. Phase one is the like the shell of the building. It's a pre-ins building. Then phase two is the ice rink. This one here on the right side of this ice rink, and then the phase three is the mezzanine floor. And then, but when we did it, all the design, of course, when you design the foundation, you have to design this one. So we did the preliminary sizing of this, give the reaction to the steel manufacturer for the pre-ins building, and then they um, analyze their building with considering this mezzanine floor loadings, and then um, yeah. So if this particular building will be designed with still like will be a steel framing, then like I showed you earlier, that it will be when we still joist in direction the same as a wood truss in our last video. So it will be framed with this one, open with steel joist, and typically this is between 4 to 5 feet spacing. It depends on the load and depends on the span, and then sometimes we will if there is a limit on the joist depth, then it will becomes it's either heavy duty open with steel joist, or we will make the spacing closer. And then the next framing would be if we frame this as a pre-engineered building. So I also prepared a, or I saved a photo of one of our projects where there is it's a pre-engineered building with intermediate supports. So this one, especially if it's like it's, the building is too wide. If it's just typical pre-engineered building, can span without intermediate support. Usually between it can span 100 feet to 125 feet. The range building can span that much. I mean, without, it's still economical. And then we had projects, I think it was 175 feet. So we ended up having a intermediate. So this is an old project um, for our US client. And what we did on this one, or what my other teammates, because um, I was, well, at first I was assigned, when I joined the company, I was assigned to anyone who who need help. But later on, I was assigned on the wood frame building. So this will be a pre-ins building with intermediate supports. And then, so this will be our frame, you know, this will be our frame. These are just in-wall columns. This is most of the time, if this is not expandable, because sometimes the client would require, or would you know think about expanding the building. And sometimes if this is, for the meantime, this is the in wall, but sometimes the client um, will plan about expanding the building in the future. So this can be designed as expandable frame. And what it means is, um, when you decide, when the the supplier manufacturer will design this particular frame, it will be designed as a clear span, or if there's intermediate support, it will be designed as intermediate support there. And then the tributary would be as if there's another bay here, and then half of that. So it will be the same design as this one. And then usually in the plan, if this is designed as expandable frame, then they will label this one as expandable. And then if this is the final layout of the building, for example, on this scenario here, these are just typical, in-wall columns, and the framing just the same as conventional framing. But for Prince building, I have here a sample. So this is a like operations building of a like municipal district here, like a county. And so there is this is the pre-engineer building with intermediate support, this one. And then Portland's. So on this particular, um, so you have here you have framing there, no, the pre-engineered building, and then Portland's will span this way. That one. And the usual spacing for Portland's is between 4 6 to 6 feet. That's their typical so far. That's the most common spacing. And then this is between 8 inches to 10 inches um, depth, four lanes, Z four lanes. So, and then so nowadays, because of the energy requirements, most pre-engineered building are now 12 inches, 4 lanes like depth. So that's 12 inches. And then so in this particular picture, you will see, so you will see the engineered frame, and then they have this bracing. So this bracing is crucial in designing the frame because this will if you provide if you provide bracing like bottom flange bracing, you can reduce the unsupported length of your framing. Then it will be economical size, and there will be because that will prevent any um, torsional buckling, like local buckling. Mm. So, for example, if this is your frame, uh, so for example, if that's your frame, so your bending here would be, you know, something like that one. So this will be positive bending here. This is negative bending. This is negative bending. And then if this is positive bending, the both the top plans will be in compression. Now, because we have purlins, that will help with the local buckling. But at at the near the hunch, near the this joint here, this will be negative bending. That means the bottom flange is the one in compression. Now, that's if you don't provide bracing, then it will require like bigger moment of inertia and be a thicker flange, bottom flange. So that's the purpose of this lateral bracing. This one, this is to brace the. So if you notice near the support, because this is negative bending here, bottom flange is in compression, right? So bottom flange is in compression. The the spacing of the bracing is really close. If you notice, it is at every purlin, and then near the midspan, it is now every other purlins. So you have to consider that one. So that's why it is important that whatever you assume in your calculation, you have to match that in your details. So if you assign a bracing top and I'm only experienced with SAP 2000 software, and then in SAP you can add bracing, and then you assign if it's top only bracing or is it bottom only bracing or both top and bottom. So and then you can specify the location. If it's for example here you already know that the spacing of the purlins will be say 5 feet. So you assign your bracing every 10 feet. And then near the support where you have a negative bending, bottom flange is in compression, then you increase the spacing. So as long as your assumption, your details matches with your assumption, then should be fine. Otherwise, if for example you assume it's a laterally braced and then you don't provide bracing in the actual. I've seen when I did a third party inspection for metal building manufacturer. This is one of the items that I really have to make sure that it matches with the design. And one of the inspection I did, I noticed at least two bracings were missing. So I told them to add that bracing, and then they can't find for some reason they can't find any bracing um, like provided by the manufacturer. So we ended up customizing it using an angle, like a steel angle. And then yes, if you have portal frames, then you have to make sure that the portal frames are correct. Diagonal bracing for your lateral frame system. Make sure it's tight because during inspection, most of the time I will notice it's slack. It's not tight, so it won't function as designed. Now, also in Orleans, because you have you have so for example, range in the building are slope, right? So it will be slope. Now your purlins is also um, in that orientation is also because it has to be perpendicular with the frame, then it will be slope as well. Now, if you notice, your wind load is perpendicular to the surface, but your gravity is no load. Your gravity load is no load collateral load that is in that is vertical like gravity. mm. So once you resolve this force, it will be resolved into a horizontal, horizontal with respect to this axis, and then there would be vertical this way. So this vertical component will be added to the wind, and then this one will be a horizontal load to the purlins. Now, because if this is, if this is your building plan and then your purlins, so your purlins is spun this way, right? This is just half of the range in the building, the other half is right here. So if that's the case, this is slope. So your purlins will bend along the minor axis. This one will bend along this axis. At the same time, it will bend also along the minor axis. So it will bend this way as well. So it will bend this way, and then it will bend perpendicular to the screen. So it will bend. So there will be biaxial bending. So in in this in, for the bending along the major axis, because this is oriented this way, it is really strong. So that's fine. What we are trying to, or what would be the problem is the bending in this direction in the minor axis, because the moment of inertia or the section modulus is small. So that's why, to prevent sagging of the purlins in this direction, most of the time you will add um, bracing or sagrad. We call it sagrad bacong. So that is in this picture. That's what you see. So this one here. So this is the actual, like, like they have different manufacturer have different style of doing this um sagrad. I've seen build manufacturers where they use cross bracing, strap tie, something like that one. And then I've seen also, like on this particular project, it is like two rods that way, up and down. And then I've seen also um uh this one, this is the most common, this one. This is the most common. And then sometimes they will just run a steel rod along the um web, this one here. So those are the three most common. But for the between the three, this one is the most common, the X bracing. So that's to prevent, one way to prevent bending in the minor axis. At the same time, it will prevent like tipping over, like rotation of the purlins. So that's how it is framed. And then so that's in the roof. Now for floor application, I, I'm not sure. Let me see. So this is the same project. Like below is this is the framing below. You have metal deck on wide flange beam, and then on top, this is the what it looks like on top. So this is a composite metal deck, and then the reinforcement. It's a welded wire mesh. So this is a mezzanine floor of an arena, like a shrink. What else? I think that's it for now. And in the next video, we will now start, you know, we will start um, doing these loading calculations, like calculate. Now, this one, um, this is pretty straightforward, like calculate the assembly, calculate the weight of the assembly if it's, if it's metal deck, composite metal deck, then the weight of the concrete and metal deck, and then whatever collateral or another term for collateral load is MEP load, any ducts, any electrical, any plumbing, that would be under collateral load, and then live load. No, this is whatever is specified in the code depending on the occupancy. And then we already discussed about this partition load. Make sure that you know the definition based on your local jurisdiction. If this is considered as a dead load, we already discussed this in the previous video. Now, in like I said, in the Canadian code, this is considered as dead load, but in the US code, this is live load. So it is important to know the definition of this load so that you can apply the appropriate load factor when you do the load combination. So, and then this is no drift or is no load. We already um, discussed about this one. Now, in the next video, we will focus on the bonding load because um, this is not common. I mean, this is only applicable if you have flat roof and at the same time if you have like a roof deck. And then we'll also focus on how the wind load is applied to a building because there was a confusion whether to use the main wind force resisting system or the components and cladding. And then seismic load also, that's pretty straightforward. Just determine the what we call this one, seismic load based on whatever the governing code or provision for seismic in your local jurisdiction. And then crane load, we will not touch this. This is special. And if you're, I already mentioned about this last time that if you are really into crane design, then you have to download the design guide for designing cranes. Um, so yeah, we will focus on these two here, and then of course we will discuss the other loadings, but really quick. We will focus more on funding load and this one, and then we will discuss because I in in my page I posted this particular where is it? I think I have it here. Let me check if I have it here. Design guide. So I so some of you already have a copy of this one. This is based on the old code. We already have 2020. So this is design and criteria, and we will discuss this one. We will discuss the how the laws are applied to this building, and then so this is complete guide. So we will discuss this one, you know, and I will also show you the spreadsheet I did. So we will discuss this one. This is for designing wall girts. This one is for cladding. So this is different pressure used for cladding, and then the primary structure, it's also different. I think I have it here. Mm, main, is it? it is. But anyway, this design guide should be read in conjunction with the National Building Code. I already told you before in a previous video that you can actually download the Canadian code for free. You can download the PDF. So if you want to follow this calculation, this design load criteria, you have to download also the NBCC 2015 as well as the commentary. So the part four in the building code has two uh, volumes. I would say volume one is the actual load, and then or not volume parts. I would say two parts. There's the actual code, and then there is the um, commentary for just specific for the part four, the structural commentary, and it discusses everything like like definition, discussions of how the coefficients are obtained like that. So it's free. You can just download it. So anyway, yeah, okay, see you. By the way, don't forget, we have a um, let me just so in Facebook, I created a group. So this one, I created this group. It's called Structural Engineering for Dummies. So if you are new to structural engineering, I would suggest to join this group, and then we will, you know, we will share and learn together, like structural design. And then sometimes I will post some stuff in this group only, and then sometimes I'll share it. But yeah, if you want to learn, or if you are new to structural engineering, I would encourage you to join this group. And then if you have questions, just post your questions, and then if I know the answers, then I will answer all your questions. So anyway, I think that's it for now. Okay, bye.